Welcome back. We're going to recap sp hybridization using the carbon dioxide molecule. We use hybridization to modify the localized electron model to account for the bonding that we observe in molecules when atoms combine to form molecules. So we're gonna describe the bonding that happens, and when you are asked to do that, you want to follow 3 steps. Number 1, you want to draw the Lewis structure, and then number 2, you want to determine the VSEPR or VSEPR. You want to determine the molecular geometry, not just the molecular geometry, but the geometry of the electron domains. And then, using that information, you can determine the hybridization needed for each atom. So let's do that. The Lewis structure for carbon dioxide looks like this. Carbon double bonded to the 2 oxygens, and the 2 oxygens have a lone pair H. Let me move this, let me center this a little bit. So now that we have a Lewis structure, we can use VSEPR to determine what type of geometry is around the central. So the carbon has a linear geometry around it, and so the max separation there is 180 degrees. So, and then the oxygen on either side have 3 effective pairs around them, and so they want to get 120 degrees or trigonal planar electron region geometry. Now, of course, there's no way to really measure these lone pairs where they are because they're just spread out. But if you use the concept and apply it there. All right, so I'm going to use a orbital energy diagram. So carbon has an s orbital in its valence shell. It also has 3 p orbitals. It has 4 valence electrons, so it looks like this. And since the s's are spherical in shape, and then the p's have those dumbbell looking things, and they're all perpendicular to each other, so you can't use a combination of these atomic orbitals and get 2 equivalent orbitals that are going to be able to separate 180 degrees from each other. You need to mix 2 atomic orbitals. Mixing will make them equivalent. So when you mix an s and a p, when you mix 2 atomic orbitals, you get 2 hybrid orbitals. That should make sense. Now they're equal in energy in between so here's energy in between the s and the p, and that's what we're shooting for. And with this, we call these sp hybrid orbitals because you mix 1 s with 1 p. Now these 2 p orbitals, they're untouched, so they're just going to be your regular unhybridized p orbitals. So now we can see what the orbital scheme looks like for the hybridized carbon. Looks like that. Now we're going to do the same thing here for the oxygen. So oxygen has an s orbital and then has 3 of these p orbitals, but it has 6 valence electrons, so 1, 2, 3, 4, 5, 6. And now oxygen, again, can't use a sphere and 3 p orbitals perpendicular from each other to get maximum separation of 120 degrees. So to get 120 degrees, we need 3 equivalent orbitals. To get 3 equivalent orbitals, we need to mix 3 orbitals. Put those 3 different orbitals in a mixer, and out will come 3 equal orbitals. That's what we're going for. And these are known as your sp2 hybrid orbitals because we mix 1 of the s's with 2 of the p's. And then this one up here is untouched. That's your regular p orbital. That's unhybridized. So let's update this. So I just did that in green because I wanted to stand out from the carbon's hybridized orbitals. All right, so carbon and oxygen have different hybridization schemes. All right, so now they're all side by side, just like up here. Hopefully you can see the connection there. Now we can describe the bonding that happens in this molecule. And I'm going to try to do this 3 different ways. One is, so this is your energy diagram, energy scheme, and then here I'll do my attempt to do it 3-dimensionally, and then down here will be the farthest at the bottom will be your Lewis structure. All right, so let's populate these with electrons. Those are your valence electrons for the oxygens. The oxygen on the left, and then these are your valence electrons. They're all unpaired for the carbon. And let's get the 6 valence electrons for this oxygen. There it is. All right, so the first I'll show you this one here in the regular Lewis structure is a single bond and a single bond. Those are your sigma bonds, your head-to-head overlap. That's going to be between these two electrons, one from the carbon's sp and one from the oxygen's sp2. All right, so I'm going to draw that three-dimensionally. I want to use just use red here. So here's carbon's, draw that a little bit bigger. Here's carbon's sp orbital. And here's, so that's this right here. And here's oxygen's sp2 orbital. Right, that's right there. So you're going to get those two electrons overlapping to form that sigma bond. So in the red here is a sigma bond. That's your head-to-head overlap. All right, now same thing on the other side of carbon. You've got that s orbital. All these hybrid orbitals kind of look the same. They look like this big lobe on one side and then a mini lobe that oftentimes books don't draw on the other side. So there's that. And then so we got the overlap of electrons in that one. So we've taken care of that. Those are your, that's right there, that's right there, that's right there, that's right there. That's your sigma bond, that's your sigma bond, your two single bonds between the carbon and the oxygens. Okay, now let's go on to the lone pairs. I'll just do this in off green. That lone pair and that lone pair on the oxygen on the left, they might be in this hybridized sp2 and then hybridized sp2. So this is all supposed to be, if we can measure the bond angle to lone pairs, that would be 120 degrees. All right, so let's put those electrons in there. That's a lone pair there. That's a lone pair there. And over here, I'll just use dots to represent that pair and that pair. All right, same thing on the other side. We got those two in the hybridized sp2 orbitals. Like that. They got maximum separation of 120. All right, and over here, down here in the regular Lewis structure, I'm just going to use regular dots. So we've got everything taken care of. All we need to do is take care of the pi bonds. So this is your sigma bond. That's your sigma bond, and the pi bond we need to do. We'll do that here in blue. No, we already have blue. Let's go with purple. Okay, actually we use, so the one on the right we'll use purple. So this p orbital is unhybridized, and that's going to form a pi bond with that p orbital from carbon, and that's going to be the overlap of two unhybridized p orbitals. Let's say this is py. All right, so we got a p orbital here on this. I should have angled this a little bit more. Now you got to imagine this is, we're going to rotate this so it's on the plane of that's going through the screen, okay? Because I need to make this one come out of the top. There's your p, and there's your py, let's say, right? And so they're going to overlap side to side, top and bottom of the axis, not between the axis, because that's where the sigma bond is. It can't overlap there. But that region there is the pi bond. Both of them, top and bottom, is one bond, right? So put the electrons there. I'll just pick them on the top here for now. Right, so there's that pi bond in purple down here on the low structure, and I'm going to pick a different, go orange. All right, now there's a px. Now going maybe this. They're all perpendicular. All right, there's a px there, the carbons and the oxygens, and that's going to be the side-to-side overlap of those two electrons, or those two orbitals. All right, and that's going to be up here. The Lewis structure is going to be orange. That's your pi bond, and that's your pi bond. All right, so over here there's overlap going on above and below the axis around it. And there I'll just put on the bottom of this one. There's your electron sharing those pi bonds. So hopefully now you can describe the bonding that happens in the carbon dioxide molecule. The sigma bonds are created by the head-to-head overlap of the hybridized orbitals. And you should also know why we're hybridizing these, because we need maximum separation to lower the energy of the molecule. When they bond, those atomic orbitals just don't work the way they are. So we've got to mix them up to get these optimal angles, geometries. That's why we use VSEPR and Lewis to start this off. All right, now keep in mind this is just a simple model that builds the foundation for more complex models, and newer models already suggest that this is not what happens, but this is a great way to build your foundation so we can move on to those more complex models.